Imagine a system that can translate languages, write code, and even compose music, all without being explicitly programmed for any of these tasks. This isn't science fiction. It's the power of modern artificial intelligence. Today, we're diving into the heart of transformer models, the architectural breakthrough that's revolutionized machine learning. If you've ever wondered how models like GPT or BERT understand context, generate text, or analyze data, this video is for you. Let's unpack the mechanics behind these systems, step by step. Let's start with the basics. Traditional neural networks struggle with sequential data, like sentences or time series, because they process information in a linear fashion. Recurrent neural networks, RNNs, tried to address this by maintaining a hidden state, but they suffered from vanishing gradients and couldn't capture long-range dependencies. Then came the transformer, a model that discarded recurrence entirely, replacing it with a mechanism called self-attention. This allows the model to weigh the significance of different words in a sentence dynamically, regardless of their position. But how does self-attention actually work? Let's break it down. Each word in a sentence is converted into three vectors: queries, keys, and values. The query for a word asks, "What should I focus on?" The key answers, "What am I relevant to?" And the value holds the actual information. The model calculates the similarity between every query and key using a dot product, then applies a softmax function to normalize these scores. These scores determine how much each value contributes to the final output. It's like a voting system where each word votes on what other words are most relevant to it. Now here's where it gets technical. The dot product between queries and keys is scaled by the square root of the key dimension to prevent large values from dominating the softmax. This scaling ensures stable gradients during training. Then, the weighted sum of values produces a context-aware representation of each word. This process happens in parallel across all words, which is why transformers are so efficient. But wait, how does the model understand the order of words? After all, a sentence like "the cat chased the dog" is different from "the dog chased the cat." Transformers solve this with positional encodings. These are learned vectors added to word embeddings that encode the position of each token in the sequence. Unlike RNNs, which inherently process sequences step by step, transformers rely on these encodings to preserve order information. The positional encodings use sine and cosine functions of different frequencies, allowing the model to extrapolate to sequences longer than seen during training. Once the self-attention layer has generated contextualized embeddings, they pass through a feed-forward neural network. This is a simple two-layer MLP, applied independently to each position. But the magic doesn't stop there. Transformers stack multiple self-attention layers, each capturing different levels of abstraction. For example, early layers might focus on syntax, while later layers grasp semantic relationships. This hierarchical processing is key to the model's ability to handle complex tasks. Let's talk about training. Transformers are trained using masked language modeling, where the model predicts randomly masked tokens based on their context. This forces the model to learn bidirectional context, unlike older models that process text sequentially. Additionally, next sentence prediction tasks help the model understand relationships between sentences, crucial for tasks like question answering. Now, why are transformers so scalable? The self-attention mechanism's parallelizability allows for efficient training on massive datasets. But there's a catch. The computational complexity of self-attention is quadratic in the sequence length. For a sequence of 1,000 tokens, that's 1 million operations. To mitigate this, researchers have developed optimizations like sparse attention and linear attention, which reduce complexity to linear or near linear. Finally, let's consider real-world applications. Transformers power everything from chatbots to drug discovery. In natural language processing, they enable state-of-the-art performance on tasks like translation and summarization. In computer vision, models like vision transformers, VTS, treat images as sequences of patches, achieving results rivaling CNNs. Even in reinforcement learning, transformers are used to model long-term dependencies in decision-making processes. So what next for transformers? Researchers are exploring ways to make them more efficient, robust, and generalizable. Techniques like knowledge distillation, where large models are compressed into smaller ones, and hybrid architectures combining transformers with CNNs or RNNs are pushing the boundaries. The future of AI isn't just about bigger models, it's about smarter, more adaptable systems. If you're interested in diving deeper, check the description for links to papers, tutorials, and tools to experiment with transformers yourself. Thanks for watching, and remember, understanding the why behind these models is just as important as the how. Stay curious and keep exploring the frontier of AI.